Today, this presentation was originally supposed to be held by my colleague, Sirkiä, but she wasn't able to attend, so I'm going to present it. And I decided to shift the focus totally on dissimilar meta-welds. I added some slides from my thesis, which I finished a couple of years ago, and now I have way too many slides, but let's see how many I have time to go through. But hold through. And hopefully this inspires you to familiarize with my other work then. Dissimilar meta-weld, it's a connection between a reactor pressure vessel and the piping. The reactor pressure vessel is from low alloy steel and the piping is austenitic stainless steel typically, and the weld is also austenitic. In this case, what we are going to investigate, it's a nickel base alloy, and then we have a low alloy steel typical. Now that's a French one, but it's supposed to be SA508, a typical low alloy steel in nuclear power plant applications. And what we have done to this material is to look at the thermal aging aspects in air. It was thermally aged for these times and at 400 degrees and 10,000 hours. It's connected to 60 years of operation of this power plant. And class 1 or a dissimilar meta-weld is a safety class 1 component, so that's why you need to have a look on the fracture properties. More closely, we are going to focus on the low alloy steel side, very close to the fusion boundary. That's where we place the cracks. So the heat affected zone in total, it's 2.4 millimeters wide. And then when you look on the hardness, when you travel away from the fusion boundary, on the low alloy steel side, there's a lower hardness next to the fusion boundary, and and then the grain size again, it's quite high close to the fusion boundary, but lower, roughly 300 micrometers further away. And the hardness peak is this area here is the grain refined region, and grain coarsening region is here closer by. And then when you even look closer, there's a carbon depleted zone close to the fusion boundary. So that's supposed to be it doesn't show the scale, but that's roughly 100 micrometers wide. So we tried to place our cracks in this region, but they ended up being also further away in the small scatter there. And then one challenge with characterization of these dissimilar meta-welds, so the fracture toughness is one is the crack path deviation behavior. So you might have crack in some region, but there might be this low toughness region, and the crack jumps to that region and propagates along that region. And then second one is the strength mismatch, which is connected to the eta factor when you assess the fracture toughness. And the crack path deviation and strength mismatch, these were accounted for in this analysis. Okay, the methods we used, we did fracture toughness characterization according to ASTM E1921. Then we had impact toughness characterization with the instrumented impact tester. There are the testing devices and FEM modeling of the eta factor, and then crack path characterization, because we have these jumps in this material. So after we did the T0 testing, or this fracture toughness testing, we located the initiation location on the fracture surface. And then we measured the distance from the initiation location to the crack tip. And then we also measured the crack profile. So as I showed you earlier, there's this jump, which is typical behavior for all of these specimens. So this way we were able to characterize the distance between the fusion boundary and the crack tip. So we got two distances which we will use later on in the assessment. And then here you can see that that's confirmation. You see that's a fatigue pre-crack, and the initiation has occurred somewhere close to the fusion boundary. And this type of jump happens in all of the specimens. So towards the results, eta factor, those who you are familiar with fracture toughness characterization, it's this kind of equation that relates the measured force and displacement to the fracture toughness. And we model this type of model with crack at the fusion boundary or close to the fusion boundary. We had different regions to simulate the different locations of the heat affected zone. And then from these simulation results we estimated the eta factor, and we noticed that as long as the crack is close to the fusion boundary, so at those distances we are focusing on in this work, it doesn't deviate that much from the ASTM solutions. So that helps us to apply the standard. But if you are way further away from the fusion boundary, then the strength mismatch condition of the different regions might alter the eta factor, and you might get even a 20% difference or 15% difference in your result if you don't take into account the strength mismatch. And then because there's this crack location problem, or soon I will show you that the further you are away from the fusion boundary, the higher toughness will be. But then we came up with this correction to estimate what the fracture toughness would have been if the crack was placed on the fusion boundary. And we used this HRR type of stress field to estimate that, okay, if you have this type of connection situation as shown here below, that you have the crack further away from fusion boundary, but then you have the initiation occurring at another plane. Then we estimate that okay, that there's certain stress at which that initiates, and then if you have this condition with the crack on the same plane as the fusion boundary and with the same stress and distance, the initiation happens. Then by using this equation you can make them equivalent, and finally you will end up with this kind of equation to correct kind of the fracture toughness. And that's the measured fracture toughness, and then that eta factor, or that is it theta, whatever. Yeah, it's this angle between the original crack plane and the initiation site. And this was the distance we measured already experimentally. And then by applying this, here's some validation. So we have fracture toughness here. It's in a different format, but otherwise it's okay. And then we have distance from fusion boundary, so location of the distance of the crack from the fusion boundary. And then we have the different conditions here. And the black lines, they are best fit based on Excel. And then the prediction that we came up with, it seems to describe rather well. We don't have that much data, but then when you look on averages, so this is the estimated T0, and then average distance from fusion boundary, you see that it's roughly located around our estimate, or this prediction. So basically what we did with this was then to estimate that if now the average crack location was 0.1 millimeters from the fusion boundary, what would the fracture toughness have been, or the T0 would have been, if the crack was located here? And that way we were able to correct the results. And these are the master curve assessment results more in detail. So you have a typical fit for the different conditions, four conditions, and you have to take into account the scaling effect, and then you have the upper and lower bounds. And not more about that. So these are the results. 2 minutes, okay. Then we have an impact toughness shift of 50 degrees, but the fracture toughness shift is 10 degrees. And the reason for that is there are many differences, but one is that we have a fracture initiation, propagation, and arrest. That's what the impact toughness test describes. But a fracture toughness test describes the fracture initiation. So we decided to look on the crack arrest forces measured from the instrumented impact tests, and we were able to generate this kind of curve, and those results show that the arrest toughness shift it's 35 degrees. So if you put the math together, the total shift, impact toughness shift is 50 degrees, this is 30 degrees, and the initiation toughness shift based on fracture toughness was 10 degrees. So that sounds reasonable, but it might not have to do anything. That might also be a consequence, so it would be interesting to have other materials to see how that connection works. But in summary, many of these results are summarized in these publications, and we investigated the different shift because of thermal aging, and fracture toughness shift gave a lower than impact toughness, and it might be connected to the arrest toughness, why there's a difference. Okay, but thank you for attention.
Thank you very much. Is there any question? No question, so everything is clear. Thank you very much again.
For sure.